Hello, I'm McToon, and it's Tuesday night. Now, I'm on vacation this week, so this is a replay of an old debate from a couple months ago that I didn't air yet on my channel. Now, this is the second debate I had with a guy called Whatsupp, and it was hosted on the Earth Awakening's Discord server, moderated by Amy Hogan. Now, this particular debate has been sitting on my hard drive, ready to go for a while, and Whatsupp thought I was scared of it. He actually put it on his channel and called it Unseen Debate with McToon, hitting like a ton of bricks. Well, it does hit like a ton of bricks. Unfortunately, like most flat earthers, he's unaware that it hit him. So good for him. I do need to add a little clarification in here. I mentioned in the debate that NAVD88, and also I talk about NGVD29, but mostly NAVD88 is a vertical datum, and I say in the debate that it's an ellipsoid. This is incorrect. I actually should have said that NAVD88 in conjunction with NAD83, the horizontal datum that's used across the United States, together is an ellipsoid. So I was a little imprecise in there. Now, I emailed David Zilkoski, the project manager of NAVD88, and got some information from him, including I got a paper from him talking about how that datum as well as the Great Lakes datum are actually the same. They merged them. And then also a fantastic one where they compared NAD83 and NAVD88 together to the geoid 18, which is a geoid which is based on an oblate spheroid, which includes variations due to local gravity, which, yeah, anyway, doesn't help the flurfs. They found when they compared those two that the elevation data for NAVD88 compared to the geoid was less than 11 centimeters in disparity. That's it. That is the largest outlier of the discrepancy between the two. Most were less than 2 centimeter differences in the entire NAVD88 network across the United States, an entire network across the United States to Alaska, Florida, all over the place. Anchored at one point, but it's a network of base stations and benchmarks across the country, thousands of them. Anyway, it doesn't help his position at all. There's a couple other things that he mentions in the debate. I try to get the links to most of them, at least the relevant ones, in the description here so you can follow along. This whole thing runs just a little bit more than 2 hours, so I hope you enjoy it.
Well, welcome everybody. My name is Amy, and we're going to have a debate today between McToon and Whatsupp. This is going to be a great debate. I'm excited about it. I hope you all are too. So let's get everybody introduced. I'm going to start with Whatsupp. Whatsupp, how are you today?
Very good. Thank you. The question, how are you guys? Because the last time we met, we left a little too early, I think.
I think so too. I think you're right. I'm excited about this one because it seems like we have a little bit more time. So this is really good. So this is awesome. So yeah. And next up we have McToon. McToon, how are you today?
I am great. It's a good day. I don't have the time constraint that I did last time, so hopefully it doesn't go too long, but I won't have to leave quickly.
Excellent. That's great. I know this is really good, and I have extra time today too, a little bit, so this is really good. No rushing today. So I hear that you wanted to start first. What's up? And you had a presentation to do?
Yes, sure. So
okay, if you want to go ahead and...
The idea was that last time I didn't have it, so this time okay. I'm bringing something.
Excellent. So if you want to go right ahead and get started, take your time, and we'll get going right on that for you.
Sure. Ready for the... So basically last time we established that we should talk about the mean sea level. And as far as I remember, we didn't really at the very core of the conversation that we had, again, last time. So this time I tried to bring something that is about mean sea level measurements. So the very first thing that I think we should start off is, what does it even mean? So anybody who's listening could have a broad idea what is mean sea level in the first place. Now, I brought two different definitions from Britannica.com and SearchWatch.com. They're basically, agreeing with each other that the mean sea level is a datum to which elevations and contour intervals are generally referred to. The other definition from searchwatch.org also explains it as an average height of the sea over long periods of time, usually a month or a year, the shorter term variations of tides and storm and blah, blah, blah. So the basic idea is that the mean sea level is only just a reference from which we are vertically determining the elevation, the height of something. Now, in America, in the United States and its territories, the mean sea level is determined by taking hourly measurements of sea levels over a period of 19 years at various locations, and then averaging all of the measurements. Now, the basic problem that you would have is, how would you determine that if you have various locations and they are differ at the very base of their calculations? But that's going to be another problem that I'm going to look into. By the way, this is from an article from National Geographic, so I guess the source is quite respectable. Now, the real problem when they are trying to determine the mean sea level is that the sea level is always changing. And for that, they, come up with the idea to have a tide gauge that is trying to measure the hourly happening tidal wave differences that happens because of the large body of water moving up and down. And basically what you see right now, I'm not sure if you're seeing it, by the way, I haven't tested it yet. Everybody sees what I'm showing. I don't see anything.
No, I don't see.
Oh, frick. I had 3 slides already. It's showing for me that I'm showing it.
Does anybody else see what he's...
Sorry, yeah, it's working for me.
Oh.
That's bad, because then I'm going to jump back because, yeah, Bebo sees it.
Oh,
and you
okay.
were seeing it on full screen, right?
You have to refresh if you can't see it, because it is working.
Yeah, I have it. I had to hit on the view live stream, so got it. Thanks.
Okay, no problem. So I'm going to be starting it again, not the whole thing. I'm just going to go through the basic idea that I showed some definitions from Britannica and SearchWatch. Then I showed a citation from National Geographic that was made back in 2011, by the way, regarding how they measure mean sea level. And then I'm here right now. Can you see that right now, McToon?
Yep.
Okay, good. So the image that you can see on the left is from psmsl.org. That's quite also a respectable source for explanations regarding surveying and benchmarks and things like that. So what I was talking about is they are using a so-called tide gauge to measure how the sea level changes over a period of time. Usually that time is like 1 hour incremental, going up and going on for the years, as I explained it before. And after a certain amount of time, and it varies for every country, by the way, on the world, but I think in the US it's about 6 years they count in, and they try to average all of the different tidal measurements and then come up with an average to that. Now that the sea level going up and down and averaging it, that is what is called mean sea level. That's why it's mean. Yeah, so I have to, one exact example for a route. Well, we could call it observatory zero datum. We can call it different things. They call it very different things, by the way. And it's from the UK. It's established in Newlyn, England. And the basic idea is that they are saying that there is a mean sea level that establishes a zero value for measuring elevation, measuring height. Is that refers to something also, because you cannot just have a zero at some point, and that's something that it refers to is just physically placed dot, basically, and that's what they call benchmark. And in England, for England, as far as I know, this is the only and the basic and the one that every other benchmark refers back to. This in Newlyn, it's sorry, I'm hearing someone.
I'm sorry.
Yeah, someone has some.
That was my wife talking to me.
Okay.
Sorry.
Okay. Oh, sorry. No problem. So the basic idea again that there is a route, a basic benchmark, observatory zero datum, they call it, and the Ordnance Survey maps are referenced. It's bold, by the way. So they made it up like, I don't know, I didn't even look it up, but a very long time ago, like 100 years ago, they established it. This is where it gets tricky, because when and after you have a mean sea level established, how do they actually calculate? Do they even calculate the elevation, or is it somehow measured? Now, when you look on YouTube, when you put it in the search bar on Google, how do they measure elevation or height? You will find like 99% of the time these kind of images going around, on which you can clearly see the mean sea level is drawn up as and diagrammed as a horizontally straight line. For example, this source that I'm having is I'm trying to find the FAO, sorry, because it's United Nations kind of source. I'm not sure about the name from the top of my head. Let me look at it. Yeah, so it's, well, it's a little bit funny, but this is one of the sources that you could go to, and you will find firstly when you search for it on Google, a Food and Agriculture Organization of the United Nations. So I guess they have some kind of a department that deals with this kind of question altogether. And find here, for example, a description about leveling. Now, two kinds of ways to measure or calculate leveling. One is direct leveling, which is a measurement. The other one is the indirect leveling, which is more like a calculation. Both pictures are also showing the distance in between you, the observer as a surveyor, for example, and the object, and drawing a horizontally straight line in between the two. If you would go on, for example, another kind of source, mapscaping.com, which is a website for some guys who started up like a little business in 2018, and they are creating and selling minimalist maps based on elevation data. They also show the sea level, for example, in this very basic diagram as a horizontally straight line. Now, what I also found is from indianexpress.com, which is kind of far away, but I wanted to include some other sources that are not Western based. This is from an article that is explaining how they measured the elevation and the height of mountains. They also refer every time to the ground as being horizontally straight line. And I included a little diagram right below the actual measurement that you would find on that article. That's the basic calculations that they are doing, because we are dealing with trigonometry in this case. Trigonometry, you can only use simple triangles, not spherical ones, not hyperbolic ones, simple Euclidean triangles. I have another source. It's from outdoors.org. It's basically explaining the same thing. How would you measure height of a mountain if you could only look at the top of it? And it's also, of course, talking about the ground as being a horizontally level straight line. What I found, by the way, 2 days ago, now that was a funny one. I just included this for the fun, because these guys, and the one on the right is like a comedian mathematician, supposedly. He has quite a big fan base on YouTube, and for some reason, he decided to make a video about the Al-Biruni method of trying to determine the radius of the Earth. And if you would look at that image, this is a screenshot from the very end of that video. They came up with the radius of the Earth as 875 kilometers. They actually went out on the street. They measured the height of a building from the ground by going at a certain distance from it. That certain distance they weren't interested in. They went a little bit farther away. They measured both time the angle of that you could have when you look up towards the top of the building. From that, they tried to determine the height of the building, and from that, they tried to determine the radius of the Earth, and they came up with like a 90% error. So I think, yeah, that's all. I'm finished. So that's the basic presentation that I wanted to start off this debate with.
That was great. Thank you very much for that. That was awesome. I actually learned a little bit about some stuff on there too. So that was really cool. Thank you. So, was there anything else you wanted to say first, or should we just get right into anything else? Or
right
rebuttal?
now, no, because the first part should be only to present your first idea.
Okay, sounds good.
Okay, so I was curious, where is there more where there's like measurements that you're going to show?
No,
you're not going to show measurements of mean sea level being flat.
Would you like to go into the part in which we are actually debating the already set topic, which is right now what I presented?
I think that's what's next, right?
Okay, well, in a regular, like, proper debate, they usually present their own side, and then they go into a certain aspect of the topic, and they try to debate it. Asking if you have something to show before we begin.
Do I have something to show of measurements of the surface of water being curved? I showed those last time. I mean, I could go through them again. Yeah. I could go through them again.
No. So I'm not
Okay,
asking for doing the same thing that you did already.
Okay, so you could just go from memory then that I showed measurements of the surface of water being curved.
Sure. Yeah, okay. I remember. Yeah, Jesse Kozlowski. Yeah.
Yep. Okay. So, and now you're happy to go into a back and forth on this then?
Mm-hmm. Sure.
Oh, okay.
Excellent.
So, it is great information that, and a lot of people don't know, mean sea level lake in the United States is a 19-year average. You showed some diagrams where they used a straight line for sea level, and I think you found that to be maybe compelling. It's just a diagram, though. It wasn't meant to display anything in relation to the surface of the water. It was just giving an illustration of how they measure the elevation. So now the people that do this survey work, the surveyors, they have their own jargon, and their jargon when they talk about the word level is that level is curved. That's the definition of level in the field of surveying. If you disagree with that, it doesn't really matter. That is their jargon. We don't get to define an entire industry's jargon. So the burden would be, if you think that level is not curved, would be then to show measurements of the surface of water, which is what they're speaking of, the surface of water being flat. And you didn't do that. And from last time, I did show the surface of water being curved. So I guess you didn't bring much there. So anyway, what they do is they take these average measurements, and then they use that.
May I rebuttal that?
Oh, sure. Go ahead.
Okay, so because we had a direct messaging with each other, right? And in that, I claimed that I'm going to bring something regarding measurements of mean sea level. That I did.
Yeah, the elevation of mean sea level. But not whether or not it's curved.
I'm sorry, I have to cut in elevation of mean sea level is 0 as a value, so it doesn't make much sense what you just said.
Yeah, but you didn't show whether or not mean sea level was curved or flat. All you did was identify the height on the shore of sea level.
There is no height. It's 0.
Well, the height is 0. 0 is a height.
That's a reference point.
Yeah.
That's the root reference point to which every other elevation ever measured is referencing to.
Yeah.
That's it.
Yeah. So what do they do with that then? Once they have the height of the shore of sea level along the shore all around a continent or a landmass, what do they do with that? You know what they do with that, right?
Maybe then I wasn't really sure, because this is really a tricky topic, by the way. If you would look into it, you would find the information to be very kind of hidden. You would have to search for it now. How you should basically imagine what they were doing at the very first time that they were trying to determine the elevation of anything is that they literally put a physical benchmark, like a little brass boat that I showed on the 4th slide, I think, at a certain point that was close to the sea. And then from that point, they were, with the tide gauges, they were measuring the difference from that point that the water gives to you, because there are tidal waves. Now, from that, they get an average, which they call mean sea level. What they do after that is that they arbitrarily, of course, conceptually, on paper, they extend horizontal plane, and then from that horizontal plane, they vertically measure the height and the elevation of what they are trying to actually measure.
Do you have some citations to that?
But all my citations were in the slide. That's why I showed you, for example, the citation from the United Nations website, or the National Geographic, or the other ones, that whenever you will see an explanation as to how they determine an elevation of something, they always assume the ground to be a flat horizontal line or plane.
Then show the citation where they actually say that they always assume the surface of the ground to be flat. That's the specific citation I'm looking for. Do you have that? That wasn't in your slides.
Written out with actual words and with those words. No, I do not have that.
Okay, so you don't know. All right, excellent. So I do know a little more about what they do with this vertical information. They put that into a vertical datum. In the United States, the older one is NGVD, National Geodetic Vertical Datum, NGVD 29. And they updated it in 88, and they called it NAVD, North America Vertical Datum 88. Both of those are ellipsoids. So if you're going to cite something as a vertical differential from a datum, and that datum is an ellipsoid datum, then you are not suggesting that the surface of water is flat. You're suggesting that the surface of water matches that vertical datum, which is an ellipsoid.
Okay, we are not talking about at that point regarding measuring elevation. You are only talking about that particular idea of the ellipsoid.
Okay.
Not how they measure elevation.
Okay. So I mean, it seems all you have is you've described how they measure sea level at one point, and then at another point, and then at another point, but you didn't do anything to marry together how surveyors deal with different points in the there's multiple points along the surface or the shore of water that they measure. So you didn't actually show what they do when they have all of these different vertical elevations or the offsets of being zero, right?
Can you see my screen sharing? Is it still there?
I see it, yes.
Okay, great, because that's literally from Wikipedia, which website I do not like, and I do not really suggest anybody to gather their information from Wikipedia. But what I did find there is
that image is from NOAA, not from Wikipedia, right?
I'm explaining where I found the image, not if the image was originally made by Wikipedia at all. But, okay, so it's the article on Wikipedia is called National Geodetic Vertical Datum of 1929.
Yeah, that's what I talked about.
So it's the NGVD 29.
Yes, which is an ellipsoid.
An attached image, that article. And as I see, even in here, it's not representing in the image sea level or mean sea level in any other way than a horizontally straight line, and from which they are vertically measuring an elevation.
So you think that this diagram, the drawing in the diagram, trumps the actual datum that is an ellipsoid. So the diagram that you found in Wikipedia completely ignores that both the National Geodetic Vertical Datum 29 and the North American Vertical Datum 88 are both ellipsoids. You're ignoring that and saying this diagram has straight lines, therefore water is flat. That's your claim?
No, water is flat by itself, regardless of what they are claiming about it.
Well, do you have measurements of that then?
I mean, of course, if I want to be precise, I would say that the surface of water at rest.
Okay, but do you have measurements of that?
I don't. This is you came up with the NGVD89. I'm showing you an image from that. I showed you like 5 different citations and other explanatory videos, screenshots, and things like that, and they are all referring to the sea level, so the water level, as being a horizontally straight line.
So because the diagrams drew a horizontal straight line, we can ignore that the NGVD29 and NAVD88 are actually ellipsoids? Is that what you're saying?
Actually, well, in order to claim that it's actually ellipsoid, you would have to have a radius, I think, for that ellipsoid.
Which, of course, they do.
At least two radiuses, by the way.
Absolutely.
For an ellipsoid.
The polar radius. A polar radius and an equatorial radius, yes, they do.
Sure. And what did I show you at the last slide? If you remember, as a joke, I inserted that one, but I'm going to show it again. So this is literally like a 3-day, but not 3, like 5 days ago uploaded video. They are doing the Albiruni. I don't know if you heard about the guy Albiruni, determining the radius of the Earth. Yes. Okay. So this is their recreation for Albiruni.
Yeah. Are you suggesting that NGVD29 or NAVD88 use the measurement from this guy?
Albiruni. No, I'm not inserting
okay,
that.
So it's about it has no impact on this particular NGVD29 or NAVD88 ellipsoids. Do you have anything relevant to that?
Since you haven't mentioned how they came up. Sorry. Since you haven't explained in any way the radius measurement itself, I went into explaining my part of it.
Yeah, so I think that the NGVD29 ellipsoid is based on the Clarke ellipsoid.
Clarke ellipsoid.
Yeah, Alexander Ross Clarke. So a lot.
Can you show it, or should I look for it?
Yeah, it was published in 1833. I can put the link in the live chat for everybody to have a look at here. There it is. And I know you think that this is an advertisement, but it's not, because I don't get any money for it. So on my website, I have 6 measurements of the radius of the Earth, including the one from Alexander Ross.
Don't say what I think. I will say what I think for myself. Thank you. I did not think that, by the way.
Okay. Well, you did say it. You thought I was advertising my website. So since you don't think that, I will gladly just say on my website at mctoon.net/r, you can look up the second one. There is the ellipsoids from Alexander Ross Clarke. That's the one that the early United States ellipsoids are based on. And then typically the European ones were based on the Bessel ellipsoid, which is the third one on that list.
Okay, great. So we got ellipsoids like the NGVD29 is actually an ellipsoid. No problem. What I did ask like 5 minutes ago is how did they determine it? How did they actually measure it?
How did they measure the ellipsoid? How did Alexander Ross Clarke survey and get the ellipsoid? The radiuses?
For example, yeah.
Yeah. So, well, being a surveyor, he used surveying techniques. So they measure typically a length along a parallel and a length along a longitude, or multiple longitudes and multiple parallels. And then they multiply that using trigonometry, because once you know, say, 1 degree of 360, if you know that length, you can just multiply it by 360. Okay. And then you know the entire, say it's a latitude, you know the entire circumference of that latitude. Then with some trigonometry, you can get the radius of the equator.
Okay. You mentioned parallel. What do you mean? What is parallel to what?
That would be a line of latitude is a parallel. Sometimes we use the word parallel instead of latitude.
I never heard that, by the way. What you just said, I never heard that. But parallel latitude lines.
Yeah, latitude lines are parallel.
Latitude lines are parallel. Now, the only geometry I would have heard about it, maybe, is the spherical one. In my understanding of the world, we are living in Euclidean 3D space. That's not concerning spherical geometry whatsoever.
It's not what?
In Euclidean 3D space, when you have a parallel, you're actually meaning two straight lines.
Yeah, but like I said,
not intersecting ever.
Surveyors have their own jargon and techniques. So when they say a parallel, they are saying that lines of latitude are parallel, meaning that they are doing these things on a three-dimensional spherical surface. So if you don't want to do measurements on that, it doesn't matter. That's what they did. That's how they did their measurements. So when they say a parallel or a line of latitude, they mean it is a parallel. So it's a circle, it's a concentric circle that's parallel to the other concentric circles on the surface of a sphere. Yeah. That's what they mean.
Yeah. Okay, I know what they mean. What I just told you is that we are living in 3D. We are living in 3D Euclidean space. Now, the spherical geometry is non-Euclidean. It's spherical geometry. The two has no real connection to each other. What they have, I'm going to present that within 1 second. It's not going to be a presentation, just a presentation of one thing only. And the real problem is that when you are dealing with different geometry and you are using jargon, they're not going to match. So what you mean by parallel, you should always add that you are talking about spherical geometry kind of parallel.
Okay, well, are you aware that there are transformation techniques between Euclidean three-dimensional coordinate systems and spherical coordinate systems?
I heard about it, but I never seen it actually carrying out without any kind of error.
Well, it's a purely mathematical thing there. So it's just depending on how many digits you want to carry in your precision. But in high school in the United States, we cover polar coordinate systems and Cartesian 2D coordinate systems, and the methods to switch between them, to transform between them, is covered in high school in the United States. Typically, spherical coordinate systems and three-dimensional Cartesian coordinate systems are covered in a university, or maybe in more advanced math classes in the United States. But yeah, it's done. There's no challenge to do it. It's very well mathematically defined. So you can have any coordinate system and transfer between them. So.
That's a great claim. What I wanted to say regarding what I'm going to present is taking up like 2 minutes more. So if you would like to say something,
yeah, go right ahead.
I'm going to insert 2 citations within, again, 2 minutes.
Okay.
1 moment, please. Amy, so far, are we behaving stuffs, by the way?
Yes.
Okay.
No interventions needed yet. You're doing excellent,
Okay,
both
great.
of you. Thank you.
Thank you. So can you see my live stream?
Yes.
So these both are, again, from Wikipedia. Again, I do not like it, but this is the fastest way that I have right now. In the section that is talking about geometry a bit, you can find on Wikipedia, again, non-developable surfaces. Now, one kind of a non-developable surface within at least Euclidean geometry, which we are in, again, I'm going to mention it again, we are in Euclidean 3D space. Spheres are having a non-developable surface. Under any metric, as they cannot be unrolled onto a plane. But the basic idea that it's not developable, the surface of a sphere is not developable. Now, that's exactly what I meant when I said that spherical geometry is non-Euclidean. Because spherical geometry is dealing with the geometry of the two-dimensional surface of a sphere. Now, those two claims, those two fields of mathematics are contradictory right from the beginning.
Well, that's some straws there. You can. Are you saying that you couldn't put something on the surface of a sphere? So, like, maybe I had a basketball. I couldn't put a diorama building onto the surface of a basketball. Is that what you're saying?
Diorama building on the surface of a ball, no problem with that. We are dealing with the Euclidean space at that point.
And you could define the coordinate system of that basketball using either Euclidean or spherical coordinate systems, either one, and you can transform between them with the formulas that have been developed quite a long time ago. So what problem
would you
is
transform in between the two because of what I just presented?
You're saying you cannot transform between the two? I'm sorry. I think you're going to need to do a little better than that. Mathematicians will definitely disagree with you that there's no transformation between coordinate systems.
Without errors, without distortions, without having any kind of problems, I cannot imagine.
A transformation between coordinate systems is not a flattening of a sphere. So that bottom one isn't what I'm talking about when I say transforming between coordinate systems. You have a point in three-dimensional space in Cartesian coordinate systems, and you have a point in three-dimensional space in spherical coordinate systems. There are mechanisms using trigonometry to transform one coordinate, an XYZ, to a R phi theta in a three-dimensional spherical coordinate system. There's no problem with this type of transformation.
May I ask you to show me the two different coordinate systems, just to, so I have a picture about it?
You want to know about the spherical coordinate system?
Yeah, and the, Cartesian one or whatever, the other one you would like to compare it to. Well, not just compare, but transform from one another.
All right.
Thank you.
All right. And so I'll share. I don't know if you have to stop sharing yours or not, but
I think we can both live stream.
Yeah. All right.
Yeah,
So there is on Wolfram Alpha, which is I would highly recommend going there instead of Wikipedia to get information on these types of topics. So here's a spherical coordinate system. You can see the center of the sphere is the origin, and you've got a radius that's going up to the right. You see that? And then you've got a theta and a phi. Or phi, depending on how you pronounce the Greek letters.
Yeah.
So that's a spherical coordinate system.
Okay.
Right? And then the transformation to a Cartesian three-dimensional, I don't know if it's in here or not, but there you go. Here it is. In terms of Cartesian coordinates, x equals r cosine theta sine phi. y equals r sine theta sine phi, and z equals r cosine phi. There you go.
Yeah, determining points with angles.
Yeah, that's how you transform between them.
And multiply it by the radius. Huh?
Yes.
How would you... the real basic problem I have with that is that, like, can you explain further? Because, okay, we have these equations, but what does it actually mean? Like, I have a point in the Cartesian coordinate system, which I haven't seen a picture or anything like that. That's what I specifically asked for, but okay. But how do you actually do that besides this? Because this is only an equation, a formula.
Well, this also has a picture of Cartesian. You see the XYZ in the diagram there.
Oh, sorry, yeah. Okay.
I gave you exactly what you wanted.
Z. What the... I'm already having problems because as far as I know, X and Y should be perpendicular to each other, and then the Z should also be perpendicular to the horizontal plane.
They all are. Yes, they all are orthogonal to each other. But because it's being drawn it's being drawn on a two-dimensional surface, you have to use a little bit of imagination.
I'm sure that the Y and the X axes are not perpendicular to each other whatsoever.
In this particular diagram, they are not, because it's showing the x-axis as coming out of the screen, but you can't actually have the x-axis leave the screen because the screen is only two-dimensional. That's typically how drawings are done in three-dimensional space on a two-dimensional drawing or diagram. This is common. It's common in high school. In America at least. I don't know if you had a math teacher that tried to draw a three-dimensional object on a two-dimensional surface before.
Many times, yeah.
Oh, okay. All right. So, what was your question?
So, yeah, that's the end of the sentence. Okay. So, again, okay. You let's say you are going from spherical to Euclidean. Now, how and why would you do that if the first basic idea is that there is Euclidean geometry and there is non-Euclidean geometry? Like that's what I'm trying to say to you, that the spherical or the hyperbolic geometry are non-Euclidean geometries. So when Euclidean geometry is referred to as, at the very end, of course, 3D space geometry that we are living in, then why would I use any kind of other geometry to determine a certain point of, let's say, in anywhere in the 3D space? Why would I use another geometry?
Well, I suppose if you're standing on the surface of a sphere, it would be pretty convenient.
But that you can do in 3D space, 3D Euclidean space. There's no problem regarding that.
Well, true.
The problem comes in when you are trying to develop a 2D surface of a 3D sphere, because you cannot.
Correct. You cannot flatten a three-dimensional sphere without distortions. But you don't need to. If you leave your coordinate system in three-dimensional space, you don't need to. If you're going to be doing things in three-dimensional space and you're doing something on the surface of a sphere, then it is significantly more convenient to leave it in spherical coordinate system than to move it to a Cartesian coordinate system, or Euclidean, as sometimes referred to, because it's easier to do things. For example, to calculate the distances between points on the surface of a sphere, the math involved in doing that using a spherical coordinate system instead of a Cartesian coordinate system is significantly easier. You use the Haversine formula when you are in the spherical coordinate system. I don't even know what the formula would be if to get the three-dimensional spherical distance across the surface of a sphere using XYZ. I don't know what that is. I've never looked that up, but the Haversine formula is, while it's got a good number of factors to it, it's not that complicated.
I don't know why you mentioned Cartesian coordinate system, by the way, because like that's the one that we are actually using, isn't it?
Because what?
That's the one that we are actually using in our everyday, especially when we are trying to.
Yes.
Yeah.
Yeah. Why would I mention Cartesian?
When you are trying to talk about the spherical geometry. Yeah.
Well, we use spherical geometry when we talk about latitude, longitude. Those
That's
are
what you use spherical geometry.
Yeah, latitude and longitude are spherical terms. You didn't know that? So by this diagram, so that there's actual the longitude in this diagram is theta. Right? You see the theta? That's longitude. And then latitude is actually a linear number instead of a degree number in essence. But you can use phi as your latitude here as well. It's 0 to 360 degrees. Typically, it's just done from the equator. So it's a little bit of a transformation to get from a pure spherical coordinate system. But that's what we use every day. Latitude and longitude are spherical coordinate systems. So why would I talk about using spherical coordinate systems?
Yeah.
Because that's what we use.
Well, let me show something for my claim that I'm gonna make in a moment.
Okay. Now, while you do that, I'll just say if the Earth were flat, then typically the azimuthal equidistant map or the Gleason map uses polar coordinate system, not Cartesian either. It has the origin at the center. You have a radius, which in that essence is the latitude. That's the radius. And then your theta, which is the longitude. So either way, we're not using, on the surface of the Earth, we're not using Cartesian or coordinate systems.
I'm really ashamed of the third time that I'm showing a citation from Wikipedia, by the way. I'm going to make that clear right now, but that's what I'm going to do. The image is probably not directly from Wikipedia, but that's where I found it. So as far as I know, this is a Cartesian coordinate system, and I'm literally only seeing an X and Y axis.
Are you sharing it?
Else. Yeah. Am I sharing it?
I don't see
I'm
it.
not sure. But one moment. Maybe now.
There we go. I got it. Yep. Okay.
So as far as I know, this is like a Cartesian coordinate.
Yeah, and generally we don't use that on the surface of the Earth anywhere. We use latitude, longitude, which is not a Cartesian coordinate system.
Well, as far as I know, longitude and latitude are also two directions.
Yes, but they're not either. It doesn't matter if the Earth is flat or spherical. Never in either of those models is latitude, longitude a Cartesian coordinate system. It's either a spherical coordinate system or a polar coordinate system.
I don't know how that's a rebuttal to what I said, but I cannot see again a third dimension in a Cartesian coordinate system whatsoever. So.
You can't imagine? Well, right on your Wikipedia page, it talks about three dimensions.
No, because it's called a Cartesian coordinate plane in the first place, so that's why I cannot imagine. By the way, the plane is a 2D.
Yeah, let me just read to you from the Wikipedia page that you got that image from. One can use the same principle to specify the position in any point in three-dimensional space by three Cartesian coordinates. Its sine distance to three mutually perpendicular planes or equivalently by its perpendicular projection onto 3 mutually perpendicular lines. In general, n Cartesian coordinates, any element of real n space, specify the point in an n-dimensional Euclidean space for any dimension n. So you can have 2, 3, 4, 5, 10, 1,000 dimensional space in Cartesian coordinate systems.
Great. What I was trying to dwell into is the using of maps, because as far as I know, that's where we actually do use longitude and latitude lines, right?
Okay.
So
yeah, but nobody
my
claims
contention.
nobody claims that latitude and longitude are Cartesian coordinates. Nobody does. Unless you, I mean, maybe you do. Maybe you are the lone rebel, the maverick who says that Cartesian, latitude, longitude are Cartesian, but nobody else does. It is either polar or spherical coordinates.
I was trying to say, by the way, and that's what I said, is that they are referencing a kind of similar system as the Cartesian coordinate system. So again, what I wanted to dwell into is the usage of the Cartesian coordinate kind of systems, like a map.
Okay.
Now, on a map, when we are, for example, trying to measure a distance in between 2 points, as far as I know, those distances are not measured in any way as a curved line.
It depends on the...
When you mention the spherical geometry.
Well, it depends on the distance.
Determining a distance in between 2 points, that's not what I ever used in my life.
Yeah. How long of a distance have you measured on a map? What's the longest you've ever measured? And then you personally did the navigation.
Back in school in geography class, I'm guessing thousands of miles.
Thousands of miles in geometry class, or geography class.
Geography class, and with a legend, of course.
Okay, yeah. and then you traveled these because you had to plot the amount or predict the amount of fuel that you needed for the course.
So I was told that those maps are precise.
Okay, I don't know what your educational system was, but I can guarantee you that every one of those maps said it was a projection. So like your previous citation where it said that you cannot put a spherical coordinate system or a spherical object onto a flat surface. That's exactly right. And that's why they use a projection.
A projection that is knowingly any kind of projection is distorted, therefore is not used.
Absolutely wrong.
For example,
absolutely wrong. All air maps use the Lambert conformal conic projection, which are a distortion. And when they're doing long navigation, if they need to be precise, there are things that a navigator must do in order to deal with the errors due to that projection. But for most shorter range flights, they don't need to do that because the margin of error is fine. And for example, when they do an air flight, they always have extra fuel, but not too much extra, because if you land with too much fuel, then you need to dump fuel before you land.
So I never heard it before, by the way, that air maps exist just for aerial navigation. And the second thing that I did hear, by the way, especially for sea navigation, so naval navigation, is using huge local maps that are made up of smaller local maps, just, stretched on a huge, like literally physically a huge fucking map.
Yeah. Correct.
Local maps.
And all of those maps. Based, and nautical maps are a Mercator projection, typically.
So. I just said local map. Those maps, the naval navigation maps, are made up of local maps that do not conform to any kind of sphere surface.
Yeah, because you need to fold it up to have it flat. So they use a Mercator projection when they do nautical maps, and they use a Lambert conformal conic projection when they do air maps. So, for example, the FAA has their sectional charts that you can get for free for all over the United States. And that's what the pilots who are flying around the United States use, is the FAA sectional charts. Those are Lambert conformal conic projections. And they all say that there is a secant, two secant lines, which is typically in the a third of the way down or quarter of the way down, and a third of the way up or quarter of the way up is where the secant line is. And that particular line has no distortion across that line. Between the lines, there's a distortion one way, and outside the lines, there's a distortion the other way. So when you're doing, the cool thing about that is if you're doing a flight that crosses diagonally across any chart, those errors equal out. And your margin of error is greatly reduced when you do that.
I'm going to respond to that in a moment, because I just realized that I should have been more clear right now, because in my mind, I've already mentioned it like 10 minutes ago, but I should have mentioned it again, that what I'm talking about, local maps using, usually, especially nowadays, by the way, aerial photography, they measure distances like a straight line in between 2 points. And that's it. No curve, no bending, no level being, not horizontal or anything like that. They are just literally what you do is measure a distance in between 2 points with a straight line. What you just said, the error correction for the distortion.
Yeah, that works fine.
Yeah, okay.
That works fine for regular navigation, especially VFR navigation, because the amount of fuel needed that would be in error isn't that big of a problem. And like I said, they always have to have extra fuel.
Cross oceans.
Sorry?
The oceans, like literally going from one continent to another, it wouldn't make a difference, right?
Well,
okay.
The all modern navigation is generally using an app on an iPad or in the flight computer on the plane, and that all uses three-dimensional coordinate systems and the Haversine formula.
I'm not sure about that in that way, but okay.
Wait, you can verify that yourself, because you could look at any of the different software. Some of it is available for free, some is for pay, but they all have the same output. And you can look at the distance that is charted when you do that route, and it'll say it's this many nautical miles.
Okay.
Then you can use the Haversine formula yourself, independent of the software, to verify that the software is getting the same number for that distance. If you find it's an error, then I would love to find out about that.
Okay. What I wanted to also mention, what you lastly mentioned, is how did you phrase it? The errors that you would get from a projection of the Earth would cancel out?
Yeah, if you do a flight across an entire Lambert conformal conic chart, so typically top to bottom, not left to right, because the distortion above the secant lines, or say outside the secant lines, I'll say, and inside the secant lines are opposite each other, that particular flight, if it crosses diagonal, will tend to reduce the errors significantly, because the amount that they're off between the secant lines and the amount that they're off outside the secant lines is approximately the same. So your error then is reduced a lot.
That's dependent on the actual flight path. Now, if the actual flight path is not going through in such a way that it would cancel out the error, then I cannot imagine what you're even talking about right now. But
okay, so
and that doesn't happen, right? So
what do you mean it doesn't happen?
Flight paths are not straight lines ever in reality. That's not how you travel.
Yeah, well, they're curved over the surface of the Earth, of course.
No. It's what I mean is that even if you would say that that's a curve, that wouldn't be a single arc with a single radius. That's not how anything moves, by the way, and especially airplanes are not moving like that. They are trying to deviate from each other. If they would have like not a crash, but just a small distance in between them, when they are crossing a certain segment above the Earth, or they want to deviate from a huge, just became to be their weather problem, like huge clouds or something like that. They are not traveling in a perfect path in any way.
Well, yeah, of course. You plan your path, and then you deal with real life situations, like you said, weather, or sometimes there's a geopolitical reason to avoid an area, like people won't fly over, Israeli airlines won't fly over Saudi Arabia. So they don't fly over Saudi Arabia. They go down to that, fly over water. Or if it's too high. So for example, the planes don't like to go over the mountain ranges in Asia because they're very high, so they tend to go around them. But that's a whole different thing. And even when they do that, they have waypoints, they plot waypoints, and the distances between each of these waypoints is calculated with the Haversine formula. If you disagree, then please do provide the formula that is the correct formula for calculating distances between points. Do you have the correct formula?
What I have is a contention that if they are working off from a projection of the Earth, then they would have distortions that you cannot count for, because that's the word. Sorry again.
Why could you not account? Why could you not account for them? What would prevent somebody
in the first place? And if you could, then it wouldn't be called a distortion.
Well, it is a distortion, whether or not you want to call it that. It is a distortion. So how would you account for that? Well, if you know that between the secant lines, there is a mathematical quantity of distortion that you can calculate. If you really need to, you can. The nice thing is, though, like I've said, the distortions are small enough that when they do the calculations, knowing full well that there is a margin of error, they include in their fuel budget for the trip extra fuel, so that if those errors are there that are adding or reducing the distance, or they have to go around because of weather, or because they have to go to a different airport because there's a problem when they're landing, they need to include all of these different things in there in the what if amount of fuel, and there's formulas for how much they do that. So all that is easily dealt with. And typically it's done ahead of time before they take off. They have to have their flight plan.
Well, if they include, and they always include, more fuel than they actually need, then that tells me that they are not trusting those mathematical equations. So
actually, they completely trust those mathematical equations, and they allow a margin of error.
Sorry, mathematics not give you any kind of error. 2 plus 2 does not equal anything else besides 4. Okay.
Yeah, but
so if you
we're
have
not dealing.
Then you should get the right answer to your problem.
Oh, but yeah, sure. It is possible to do that, and when you use the Haversine formula, that's what you get. But when you're doing short routes on paper, which isn't commonplace anymore, most navigation through air is done with a software and is using the Haversine formula, so the distances are more accurate. But when they were doing it just with Lambert conformal conic maps, they dealt with that. There were mechanisms and procedures that they used to deal with those things. So I don't know what your problem is. You are claiming things about navigation, but you have not provided any evidence, and it seems that you don't quite understand navigation. So if you think that the Haversine formula is wrong, then go right ahead and show what actual formula is the correct way to measure distances between points on the surface of the Earth. Lacking that, you don't have anything.
They're already done that, by the way, basically. Now, again, you claiming things like that shouldn't be a part of the debate whatsoever. So you standing up and claiming that you don't have nothing is kind of, below the belt. But let's move on from that.
Okay.
So The Haversine formula, what is it about? Could you just, vaguely explain it to me?
What is the Haversine formula? It's the formula used to calculate distances between points on the surface of a sphere.
So we are back again to spherical geometry, right?
You specifically asked me to explain to you the Haversine formula, which I just did.
Asking if it's based on the spherical geometry.
Yes, it is.
And then we are back to the part that I already mentioned and explained thoroughly then later, that the spherical geometry is non-Euclidean. It's not in 3D space. Therefore, I wouldn't deal with it ever regarding anything reality.
But pilots don't give a damn about what you would do or not. They actually use the Haversine formula. It is a three-dimensional solution, right? The surface of a sphere is a two-dimensional space, and the distances between them can be calculated using the Haversine formula. That's what pilots use.
Again, I would never use something non-Euclidean geometry.
It's a damn good thing that you're not a pilot. So if you ever were to be, trained to be a pilot, you would figure out pretty quickly that you're going to need to use the Haversine formula.
So that's my basic rebuttal. Again, spherical geometry is not a reality whatsoever.
Well, so you say.
Conceptual geometry.
Well, yeah, all geometry is conceptual.
What I just said. Every mathematician agrees with that it's conceptual.
Yeah, all math is conceptual. Yes. And then you map it into meat space, and you find out that there's always a margin of error.
Geometry, not mathematics.
Geometry is a subset of mathematics. Are you unaware of this? You have to know that. You can't be confused that geometry is not part of math. You cannot be confused about that, can you?
Yeah. Spherical geometry is conceptual altogether, not based in reality. The one that is based in reality is called Euclidean geometry.
That would be a claim I suppose you could support by showing us supporting evidence for that, I guess. Go ahead. I'll wait.
The spherical geometry is conceptual. Sure.
All geometry is conceptual. It's purely math. That's all that geometry is.
You said mathematics is conceptual, and that's not what I said in the first place. But never mind. Now you're saying any geometry is conceptual. That's not really, by the way, because geometry, the word itself means metric of the geo, which means, geo meaning terra, or meaning the ground.
Okay,
and
so the definition that you're going for the definition is all that it means everything. Then definition means everything, or can we? Obviously not. Geometry isn't. Just because of the definition of the word doesn't tell us reality, right? Is reality Cartesian or spherical coordinate system? It can be represented with both, but they are all conceptual.
And geometry is earth measuring, nothing else.
Really? Well, tell that to math teachers that teach geometry and don't teach earth measuring during geometry class.
I tell you one better, they told me what I just told you. So.
Okay, so all this is just, you're trying to get off into semantics and definitions. But the problem that you still have is that none of this that you have is based on, has any measurements to support it at all. And you want to suggest that mean sea level is flat, but you didn't actually show that. You just defined what mean sea level is. You want to say that somehow you would not use the Haversine formula to calculate distances between points, but in reality, pilots do use the Haversine formula. So it doesn't matter your opinion on it because they don't care about your opinion. None of them are going to ask you whether or not they're going to keep using the Haversine formula or not. They're going to keep using it. So do you have anything to support all of your points here other than just trying to lay down that geometry means measure the Earth?
That's a very good point in the first place.
Maybe you have a measurement of the Earth. That would be novel.
Can you not cut in every time?
Sure.
Like for the past 15 minutes you were cutting in. Thank you. So I'm going to refer back to my presentation that I had at the very beginning. Can you see maybe my live stream?
Yes.
Okay. So the very basic idea regarding what you just said, or me at least, and as far as I can tell, for the measurements of, let's say, an elevation and the height of a mountain, is literally based within Euclidean geometry altogether, because that's where you have the logarithm table for a triangle from which you can determine, for example, based on a drawn diagram of the reality, the height of the mountain, for example. It's coming from Euclidean geometry altogether, not from spherical, not from hyperbolic, not from any kind of else geometry. The Euclidean geometry.
And you're showing this, the citation, the supporting evidence for the citation? It looks like you just have a diagram of Cartesian coordinates from, is that still the one from Wikipedia?
I'm showing something else. So if you see that,
okay,
then you maybe have to refresh, as Emma told you before.
Yeah, it's just spinning.
Okay.
I don't know how to refresh.
Okay, then I'm gonna do a stop streaming and restart. Yeah, I see the preview. No?
For some reason, it's not.
View.
Oh, there it is. Okay. How elevation is measured. Okay.
Mm-hmm. So, what I said before, do you remember what I said for the past 3 minutes?
Yeah, that they use this triangulation and
kind of. Well, you know, if we would want to go into the technicality, then triangulation means a little bit different thing, but this is also could be called triangulation because we are using triangles. I mean, at this point, I mean surveyors do use, and they did use whenever they wanted to only calculate something because they didn't want to go such heights for, you know, obvious reasons.
Yep.
This one is, which one is this one? Let me look it up. I'm not sure if it's the Himalaya or not, but I'm going to look it up. One moment. Oh, Mount Everest. This one is the Mount Everest, by the way.
Which one is?
In the article that the image that I'm showing is from an article that is describing how experts measured a mountain's height. And in this case, they showed Mount Everest.
So you're saying this is how,
so again,
you're claiming this is how surveyors do it.
Yep.
And the article will say this is
from
how
time to
surveyors
time.
do it.
This is
And this is
from
how
time to time. This is exactly how they do it. Yeah.
When the height of Mount Everest was measured, this is the mechanism they used.
That's what the article is explaining to you. Yeah.
All right. Well, I hope to see Everest in there. 7103 688.
So that's my basic rebuttal, that they are using Euclidean geometry whenever they are measuring, for example, elevation. But that's what they use when they are trying to determine a distance to something also. That's when I was talking about the maps, you know. That's basic Euclidean geometry right there. without any kind of curving path.
Can you put that link into the live chat?
Yeah. Live stream too. What the?
Did you put it in? Oh, yeah.
Oh, not yet. Now.
Okay.
I was copying from PowerPoint and it wanted to copy paste in a PNG. I don't know why.
Oh, I love this. All right. So that's
just, one example. I showed you again, 5 different more. I'm not going to do that again because that was the presentation about presentation. Yeah. I wouldn't call it a presentation, but.
All right. Well, let's read here. In a new measurement, China and Nepal have announced Mount Everest is 86 centimeters taller than the 8,848 millimeter accepted globally so far. How was the original height calculated by a survey of India? What does the revision mean? 2 of the senior most officials of Survey of India explain in an interview to the Indian Express. That's fantastic. The basic principle was used earlier, and this very simple, uses only trigonometry, which we're familiar with. Do you want me to stop reading? Go away there. So the principle can be applied for measuring height of an object that does not offer convenience of dropping measuring tape from top to bottom if you can't climb top of a mountain to use a sophisticated instrument. Very nice. So this doesn't give a whole lot of detail, but that's pretty cool. There's no GPS or satellite in the 50s. Yep.
What happened, in my, not just opinion, I'm almost 100% sure, is that what I'm showing right now in my live stream is the modern day Alberuni fence slide that I have. These guys actually did the same almost. They went out and they measured the height of a building with the same way. Now, what they did is trying to measure, an angle from their eye level towards the top of the building. Now, when you do that, you do not have those referred sophisticated instruments. Now, that's when you have the error of, how much was it, 86?
Yeah, and that's a great lesson.
Nothing else.
Yeah, that's a great lesson because I've watched the whole video, and it was a rather sloppy measurement. It was comedy, like you said. He's kind of a comedian. He actually cut out his arm length things, put it onto a pad, and then stuck them to his shoes, and then walked along half a block along the streets of London. Yeah. So the measurements that they used were very poor, and then they weren't able to actually bring the device that he made up into the viewing tower of the shard because they wouldn't let him bring that up there. So the measurement, the angle measurement, the dip measurement from there wasn't very accurate either. It was only accurate to 1 degree.
Not even close to accurate.
Yeah. So the lesson there is sloppy measurements give you horrible results. Garbage in, garbage out.
Great. So when you presented the Jesse Kozlowski thing that you had, using a theodolite and measuring an angle. Now, would you ever think at least that Jesse Kozlowski did something at least, again, similar, and then not counting in any kind of refraction at all?
Well, first of all, to compare from the top of the shard, their margin of error, their precision on the measurement was 1 degree, giving them a plus or minus 0.5 degree margin of error minimum. Jesse Kozlowski used a theodolite that's accurate to 1/3600th of a degree, giving the margin of error as half of that. but he did multiple measurements, giving a smaller margin of error than that. So comparing the margin of error of those two measurements is pretty interesting. Jesse's was very, very precise. Second, he did not, in fact, include refraction in his observation, but that doesn't help you. I think we covered this last time. Refraction causes distant objects to appear slightly higher. In order for the Earth to be flat from his measurements, then refraction would have to cause distant objects to be a good deal lower, which isn't what we see. And like I think I mentioned last time, there are many previous measurements of the effects of refraction over the surface of the Earth in different environments, different temperatures, different times of day, different surfaces. On my website at mc2.net/refraction, there's a large list of refraction measurements. So if you do want to
remember what was my rebuttal to that?
What your rebuttal to that was that you expected all measurements to have a zero margin of error, I believe.
No. That's what you said. I never said that, by the way.
Okay. And what is your rebuttal to that then?
Well, the rebuttal, you just said like 4 different things, right? My rebuttal, what I was trying to ask you right now, was towards the claim that refraction would only make an image to appear higher than it is. That claim I have, since then, by the way, I have never found a citation whatsoever for.
I second that.
Who's that?
Crooks. Sorry, this is an event. Could you mute yourself for a little while?
Yes, sir.
No problem. Thank you very much.
So, well, I did I not give you the citation last time to my website? Because there's a lot of opportunities for you to look at citations there of refraction causing distant objects to appear slightly higher.
But your claim is that it always happens that way.
Yeah.
That I have not found anything regarding that. Even, by the way, the other part I haven't found anything for.
I'll say that it doesn't always happen that way. And I think I made that clear last time. There are conditions where you can have the vertical stacking of index of refraction go the other direction than normal. And when that happens, though, it's a very, very rare condition. And there are significant other effects in the atmosphere that are clear when that happens. Typically, you will see miraging, multiple layers of miraging. You'll see different optical effects when that happens. In normal conditions, we can just look at the observations and see that is likely not happening.
This kind of vague phrasing when you say it's likely not happening and blah, blah, blah. Mate, whenever, for example, as I said last time also, Jesse went out and made his measurements. I'm fine with that. But when he's trying to create a geographical, physical form based on an apparent measurement, now that's where my problem comes in.
Oh, so all of your measurements must be a physical measurement and not an apparent measurement. I do remember that was from last time. So do you have any of those of any sort?
No, mate, that's not the problem. The problem in the first place is that you think that there is always refraction, right? That was one of your points last time.
Absolutely.
And therefore you cannot take anything for granted, just like that, because there is always a refraction. Now, the problem with that is that you seem to suggest that you are the one who is measuring something. Is that true?
That I am measuring something? No, Jesse measured it.
Mm-hmm. Okay, so Jesse was the measurement device. I have never heard that before.
What do you mean? Jesse was the measurement device? He used a theodolite.
Yes.
Do you not know that you
theodolite is measuring, right?
Yes, the theodolite measured it. What's wrong with
Therefore,
that?
when you are saying stuff like you are measuring something, but you are also in the atmosphere, of course. Therefore, you have problems. It's not you who is measuring anything. That's why it's called a measurement, because we are using measuring devices for that, which will tell us.
Yeah. People know this. I don't know why we're covering this.
The huge fucking strawman regarding that last time.
Okay. So, what's your point?
My point is that the measuring devices are not wrong in any way. But what you are trying to do when you are measuring an apparent thing and then claim that the apparent thing is physical, that's nonsense, because you haven't measured the physical thing at all.
Yeah, but you don't have any measurements of the physical yourself to offer.
The best way, in my opinion, especially, and I'm looping it back to the very beginning of my presentation, is the mean sea level. Now, you could call that sea level. Also, you could call that water level.
Okay.
My device would be a water level.
Okay. And how would you look at two distant water levels to see if they're at the same plane? How would you do that? How would you determine if two distant levels are the same?
Distant levels, you mean one end of the water level and then the other, right?
Let's say you set up along the coast of some landmass, 100 miles long or 10 miles long. How would you determine the relationship between the different water levels to see whether or not they are in fact on the same plane, or if they are on something other than the same plane? How would you do that?
Since we just established that just by looking at something, especially that is over a distance of miles, we couldn't determine anything because we know it's just an apparent, and it always changes. Well, no matter how you can claim that it always changes in a way that it actually rises from the physical point. Like that's what you actually claimed like back a few minutes ago when you said that it's the best atmospheric refractions are only rising the image. Therefore, the physical is actually below always than what you see. Now, that's complete nonsense in my opinion. But the other thing, again, how I would measure it is just by logic. If we claim that the horizontal plane is established by water at rest, which is the mean sea level, which is coming from sea level, then I have my proof.
But how did you determine whether or not the surface is curved or not? How did you measure that?
Surface of what?
The surface of water. How did you determine that the surface is curved or flat? How did you measure that?
It wasn't me, by the way. It was surveyors who determined to use mean sea level as a horizontal plane for the reference of the elevation measuring.
But they put it into NGVD89, which is an ellipse, or NAVD88, which is an ellipse. That doesn't help your point. Those are ellipses. Those are curves. They put those into curves, not planes, curves. So how do you think that the surface of water was determined to be flat? How did that happen? Where are those measurements? Because you can't go and claim NGVD29 shows flatness because it is an ellipse.
Wait, the NGVD29 is just a diagram. It doesn't show anything.
It's not a diagram. NGVD is an ellipsoid datum. It's an ellipsoid. It's mathematical datum.
Datum is actually the benchmark in physical reality, by the way. That's the vertical datum. I was trying to be very explicit and clear about that in my presentation, by the way. The actual vertical datum is a benchmark in reality. It's physically right there. What I showed you, England, Yolin, there is a vertical datum that is called a benchmark, and that's what the benchmark is, and that's what the vertical datum is, not an ellipsoid or a drawing of an ellipsoid in any sense.
Okay. So how did you determine that it was flat? How did anybody determine that it was flat? Because there's a diagram?
Benchmark.
Because the diagram has a straight line on it? Is that how you determined it was flat?
The claim is
the benchmark.
Right. Who was interrupting there?
You mean the benchmark? If the benchmark
hold
is
on,
flat,
hold on a second. Hold on a second. We have somebody interrupting.
Okay.
Yeah, sorry about that. Can whoever that was please mute? Thank you. I appreciate that.
All right. So I didn't hear your answer. I'm sorry. How did you determine that it was flat?
I asked you, what do you mean by it was flat? What was flat? The benchmark?
Well, you seem to think that the surface of water is flat. And I'm asking, and then you referenced mean sea level. How did you determine that mean sea level was flat? How was that done?
It wasn't me again. It was the surveyors who
I don't care. Yeah,
that the mean sea level establishes a horizontal plane throughout the continent.
Where does it say it establishes a horizontal plane? Bring that citation up where it says it establishes a horizontal plane.
In every image that I showed in my presentation,
none of those
referring to mean sea level.
None of them said
straight
that.
Line.
None of them said it establishes a horizontal plane. It just had a diagram.
Oh, they just show you. Yeah.
Yeah.
I think that's better right away.
So if a diagram is all we need, then I got lots of diagrams that show the surface to being curved. But diagrams aren't reality, right? Measurements is how we figure out what reality is. So do you have anything from reality, measurements of the surface of water being flat?
Do you remember why I brought up the orbital in the first place like half an hour ago? I asked you when you were first mentioning the NAVD89 how the radiuses were actually measured.
Yes.
Then I haven't heard an answer to that, by the way.
The answer I gave already
but I haven't heard.
Yeah, you seem to forgot Alexander Ross Clarke's ellipsoids, 1933. 1833.
That's another ellipsoid. I asked for measurement, and could you explain it then?
And I gave you, I pasted the link to his publication in the chat. And if you want, I can bring it up and we can start looking at it. But it's certainly a lot more reading than would be useful to do during a debate like this.
These kind of measurements are not that hard to explain, especially vaguely. And that's what we are trying to do here. Not you, neither me, are professors at a university right now. We are just talking.
Yeah, I'm just referencing the measurements that other people have done. So I put in the chat there, the Alexander Ross Clarke, 1833. It's called Account of the Observations and Calculations of the Principal Triangulation and the Figure, Dimensions, and Mean Specific Gravity of the Earth as derived therefrom.
Okay, but again, what I'm interested in is how the measurement was actually carried out. What is the basis for it?
And I covered that both last time and already today, but I'll do it again. They measure sometimes multiple, sometimes just one, longitudes and latitude lines. Then they use trigonometry to get the radius, the circumference of that particular line of latitude or line of longitude.
What do you mean by measuring lines?
A line of latitude. Do you know what a line of latitude is?
It's a great circle altogether. So what do you mean by measuring?
A line of latitude is not a great circle. Lines of longitude are great circles. Lines of latitude are parallels.
You were right about it.
Yes, they're concentric circles.
Yep. Well, in your model, by the way, it is, isn't it?
It is what?
It comes out as a great circle.
Longitude.
The spherical geometry.
Yeah, lines of longitude are. Lines of latitude are not great circles. Just the equator line of latitude is a great circle. All the others are not great circles. So you measure a portion of a line of latitude, say 1 degree to make it easy, and you find that it is a certain distance. You multiply that by 360. That gives you the circumference of that particular line of longitude. Then simple sine cosine, you can get the radius, the circumference of the equator. So that would give you the equatorial circumference, which you can get the equatorial radius. Same thing for a line of longitude. You measure a certain portion of it, say 1 degree. Multiply that by 360. That gives you the circumference of the entire line of longitude. That gives you the radius. So that gives you your two radii, the polar radius and the equatorial radius. That's how you get them.
So then it's a great circle, isn't it?
Only the lines of longitude are great circles and the equator.
Let's just say I was right, okay? Just because you couldn't get it the first time, I was right about that, okay? Now, the problem is that you are representing something that you think that it should work in that way. The very first thing is the longitude line is actually the circle. When you say circle, it's 2D to me. Not in any way.
It's a circle
2D.
on the surface of a sphere.
Circle, it's 2D. The 2D shape.
Wouldn't it be a straight line on the surface of a sphere?
I'm going to mute him myself, so I won't hear him in the future
Okay.
when he interrupts.
Yeah, if you'd just give me a second. I'm not sure who interrupted or if you know what's going on here, but everyone is not to interrupt.
That was Crux Ader.
Okay. No. Yeah, no talk. Yeah. Yeah, that means go on mute. Yeah.
Yeah, sorry about that. It's a debate going on. Thanks, Rakia, too.
Thank you.
So a circle, which that's what lines of latitude are, is concentric circles. So you asked how they got the radius, and that's what I explained is how they measured the radius when they're doing these triangulations.
Every circle has a radius, no problem, but it's still just 2D. And I'm agreeing with one of the circles that you have, right? I'm not agreeing with the other one having as a plane and as an angle. That's what I'm not agreeing with at all.
Okay. Well, you asked how they measured the radiuses. That's how they did it. So if you disagree with how surveyors do their work,
system in 2D. That's what I'm telling you.
Yeah, if you disagree with how surveyors do their work, I suppose you could go read up how they did it and go to different surveyors and say, you're doing it wrong, right? If you disagree with how they do it, but that's how they do it. And they've been doing it using similar methods for hundreds of years. So that you asked how they did it.
I myself have explained with citations what surveyors do in my presentation that happened, I don't know, more than an hour ago. So
actually, none of your stuff was directly talking about how surveyors did. It wasn't documenting. It was like the one from India wasn't actually, this is the instructions for how surveyors doing it. It was based on an interview with surveyors. So it was a fluff piece written.
So that was one example out of 5. So
yeah. So it was that one example was directed towards a non-surveyor audience. But if you want to talk about how surveyors actually do it, the documentation that I gave you would go into that a little bit. A better one, because the detail is immense, is the Transcontinental Triangulation and the American Arc of the Parallel, published in 1900.
Sorry, the what?
The Transcontinental Triangulation and the American Arc of the Parallel. In that one, they measured across the...
Triangulation.
Transcontinental Triangulation.
Okay.
And the American Arc of the Parallel. Now, parallel means line of latitude again. So in there, they go into great detail for how they did it. A lot of the surveying publications don't go into detail because how you do your work is different from the results of your work. Right? I write email software. My source code is not included in the filtered emails. Right? The output of my work is not. It does not include the details of my work. And so many of the surveys don't include the details of their work. For that, you would need to go to the surveying documentation and instructional textbooks, which there's plenty of those available as well.
Thank you for that information, by the way. Can you look at my live stream again, please?
Sure.
Do you see where it's at? It's back at the...
It's spinning again. Can you just stop and restart again? Because I was off on a different screen.
This tricking everybody all the time. Maybe now?
It looks like it's trying. I'll give it a little bit longer. But that's the one from is that the one from India, right?
Not that one. Not. I have on the slide another image that I would like to show it to you. Okay. If you can see.
It's still not coming. Discord's a little funny sometimes.
Yeah, ask Amy, maybe. Do you see it?
Yeah, I'm getting the spinning thing too. I think it's Discord, honestly. You could always try refreshing and see what you can do there. Yeah, if it's okay.
It's interesting because for me, it's also at the very beginning when you click it, it's just spinning and then it to me.
Exactly, it does that.
Now.
Okay, thank you.
I see you're sharing again. And I see the low-res version of it. Oh, yeah, that's a different one there. But yeah, the high-res just doesn't... Maybe if you dropped... can you change the frames per second? Because it says it's 30 frames per second, and you're just showing a static image, so lower quality would or lower refresh rate would be just fine.
I do that from Chrome because that's what I'm using, and it doesn't give me that option.
Oh.
I think on Chrome you cannot do that.
You're not using the Discord app?
No. That usually gives me more errors than the Chrome version. I don't know why.
I get the same issues. Yeah, interestingly enough, I get the same issues with it. So yeah, I understand that.
Maybe is that from a citation? Can you just drop the link in the chat?
Okay, you know what? I'm gonna drop the not the hard one. What was it? Why is it not showing just as a link? Oh, it's a PNG. Why? Why is having a transparent back?
Transparent background PNG.
Freaking.
Okay.
But
yeah, so yeah, it's just SOHCAHTOA, right? Sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So what
we know this. I reckon you know this. So that's not my contention whatsoever. My contention is when you mentioned triangulation, because triangulation is using these functions that you could find within a triangle. Now, that means that those sides that you would measure in reality, by the way, are straight lines.
Okay. And?
It's not supposed to be on a curved surface whatsoever, because otherwise it wouldn't work.
Okay, show me an actual example of how surveyors do their work then.
Well, when you mention triangulation, I'm going to show you a triangulation regarding surveying. I think I have seen that somewhere, so I'm going to find it again. Easier to screenshot than make it because of the PNG. So, for example, it's a simple kind of triangulation. And as you can see, they are always using simple Euclidean triangles. Now that means that when you have if you would click on the image, then you will see a little bit better what's written on each side. Now, they are calling calculated distances, calculated this, calculated measured angle, blah, blah, blah. All those sides are always made up of straight lines, which means that these distances, as I mentioned before when I was talking about the maps, distances are measured as straight lines and nothing else. No curve whatsoever.
Yeah, so it's a straight line.
The triangulation wouldn't work.
No, actually not at all. There's no problem at all. So these are straight lines from an elevation above the Earth to another point that is elevated above the Earth. There is no problem with these lines being straight. They aren't actual along the surface of the Earth, curving with the Earth. These are points in space above the surface of the Earth. Straight lines, no problem. What do you got?
Of the Earth. Yeah, but they are referencing the Earth itself because it says distance. Yeah, and in your model, you have the distance as a curved line.
Yes, the distance across the surface is a curved line. Correct. But they're not using the triangles.
And it shouldn't work.
It works just fine. But
using the triangle.
Go ahead.
Then what is
show me
in the first place.
Show me the mathematical proof that would not work, I guess, would be your next thing.
What the Euclidean geometry is using a triangle which has straight sides. In that Euclidean geometry, you can find correlations in between the sides and the angles within a triangle, especially, by the way, a right angle triangle. You can find in any kind of triangle within Euclidean geometry. Now, in spherical and hyperbolical, you cannot.
Okay, we'll show the mathematical proof of that then.
The proof that you have to use
you have claimed triangles. Yeah, you have claimed a whole bunch of things about spherical geometry that mathematicians disagree with. So it's on you to provide the mathematical proof that you can't do triangles on the surface of a sphere, I suppose. Go ahead. Are you saying that you cannot do triangles on the surface of a sphere, that spherical triangles do not exist? Is that your claim?
When did I ever claim anything like that?
Okay, so well, I mean, because you're saying that you can't do triangulation on the surface of a sphere. That's your claim, right?
My claim is twofold, that that kind of triangulation would not use any kind of sine and cosine functions that you would find in Euclidean, because it's not Euclidean. It's that easy.
So you don't actually know a whole lot about spherical geometry, do you?
That's what they are using, mate. When they are having one side for the triangle, meaning one distance, and a certain angle which they get from, let's say, a theodolite, then they are going on with the Euclidean geometry from that. Euclidean, not anything else.
Well, that would be where you're wrong, because they're using they use spherical trigonometry at times. It depends what their purpose is and their margin of error that they need.
They are not using sine, cosine, and other functions that are
Sure they
low
can.
signs are within Euclidean geometry.
Well, let me just. I guess it's free education time for you. Oop, hold on. I was in the wrong chat there. Okay.
Because again, if they are not using that, then why didn't they use, let's say, in this image that I posted, but I can show you others, of course, anytime. Why don't they use curved lines at all? Well, how is that a representation of anything then?
Here you go. Well, I mean, your diagram is just a diagram. It's not actually, what they use in their coursework. When somebody teaches a course on these things, it's not, they don't use that diagram and that's the end of the course. They actually do a little bit more than that. But here is a from Wolfram Alpha or just Wolfram, not Alpha, on spherical trigonometry. And there are functions that use sine and cosine in spherical trigonometry. You see that? There's angle A, angle B, angle C, and line A, line B, line C, and the radius R. There are relationships that you can do to solve triangles that are spherical triangles. Spherical triangles exist. Spherical trigonometry exists. You can use trigonometric functions to do your math in spherical trigonometry. So I don't know why it seems that you think that this doesn't exist, maybe, but maybe I'm putting words in your mouth. But you can see here is
I said they don't use it. I didn't say it doesn't exist. I said they don't use that.
Well, that would be wrong then, because like I said in the book that I referenced, the principle, the triangulation of the American arc of the parallel, they do use spherical trigonometry. So that's easy to show is wrong.
Okay, I just posted something in live stream too, again. And there's
future theorizing, continue with confidence. What's the date that comes in your mind, or the character, or the proof itself?
Well, I mean,
sorry, actually I went the wrong. I heard.
When was it done? I'm trying to find a date, 1899, by the way.
All right. So you did you put something? Oh, there. Oh, yeah.
See, in this kind of diagram that was, drawn up by surveyors.
Okay. And
simple triangles. Nothing else.
Does this show the math that they used, or is it just a couple diagrams again? You think that diagrams is it, huh?
Oh, this is like a simple orthographical view of the land and then putting on some actual triangulation, because this is how it's done.
Okay. And do you have any of the results of this particular survey?
Also, by the way.
Do you have any results of this particular survey?
I need to know that when I'm only talking about if they are using triangles or not.
Yeah. And so how do you know whether or not these triangles are spherical triangles or planar triangles?
Mate, because that's how it's drawn up. Like, it's that easy.
Because
you can see
because of the diagram again. You think the diagram is all that matters. Yeah. So forget what they actually did. Forget the actual work that they did, and let's just look at the pictures. That's this one. That's what you want?
It's called a triangulation map. This one is actually not just a diagram. This is called a triangulation map.
Yeah.
That's not just arbitrary drawing that you make at home in Paint.
Yeah. It's a triangulation map. Yes.
Actually, what they use
absolutely.
to determine certain distances.
Yeah, and surveyors, when doing these large triangulations, use spherical trigonometry. Like I said, in the book that I referenced, goes over some of these details. So do you have the Shelton base net citation? I would love to see that. Do you have that?
You want me to
So it's
present something that is a written text, and signed by blood, that they are only using simple Euclidean geometry.
No, I want the citation, because I'm pretty sure the citation will talk about the measured triangles and the actual numbers of the measured triangles.
The actual numbers are somewhere in there. I'm not sure what they are referencing, by the way, but they are there. I'm not a surveyor. I cannot read a map like this just off the top of my head. I would have to look it up, of course. But this is how the map they are using for triangulation looks like. And all I see there are simple triangles.
Yeah, and how would, if they were going to draw on this two-dimensional surface a spherical triangle, how would they draw it?
Spherical. The surface of sphere cannot be developed. That means
absolutely. So they could not actually draw a three-dimensional spherical triangle on a two-dimensional surface. They could only use a representation of it. So you cannot look at the triangles that they drew and determine whether or not these triangles are spherical triangles or planar triangles. What you need to do is look at the actual measurements of them to see if they sum to more than 180 degrees. Did you do that?
What I do know is that if you are using simple triangles, but you have the supposition that the surface is actually curving, then you shouldn't come up with the right calculation for any distance, especially over long distance. You cannot.
Absolutely, and they always use, for long distances, spherical trigonometry.
No, this is what they use, and this is not spherical geometry in any way.
Oh, well then show the measurements. Let's see some of these
the measurements of what?
These triangles, to see if they sum to more than 180 degrees or not. What do you think?
Wait a second. Are you trying to claim that if we would actually measure any triangle within that map drawn up, we would come up with a triangle that is not having 180 for its inner angles as a sum?
That's my question to you. Did you look at them before you cited this?
Wait, if you are connecting 3 points in a series
on a plane,
give you a triangle.
Yep, on a plane, and they summed it on a plane. They summed 180 degrees. On the surface of a sphere, they always sum to more than 180 degrees. That's how spherical triangles work in spherical trigonometry.
This is not a spherical triangle that you are looking at. This is a map. That's what I'm trying to tell you.
That is definitely what is in contention, though. Because you didn't actually look at the details. But tell you what, let me show you, because I don't know the details of this one, but I do know the details of the one that I previously cited. I'm sharing that right now if you want to have a look at it. These are the actual triangles. Do you see that?
This is the map that the surveyors actually use. You are supposing that they use something else also. That's not good.
Do you see what I'm sharing?
Just to let you guys know, there might be a lag or something. Oops, can you hear me? I'm sorry to interrupt, guys, but I just want to let you know there might be a little bit of a lag. We're getting some over talking on both sides, okay? Just wanted to check in and let you know.
Okay.
Thank you.
So, what's up? Are you seeing what I'm sending here?
Sure. Yeah.
Okay, so this is a similar diagram to what you showed, right? A triangulation net. Right? You see that? And here are the actual measurements. Yeah, sure. You see here, Ibapa, Pilot Peak, Ogden Peak. We can go back to this one here and we can find all of those points on this. On this particular one, right? Or other ones in the book. I think this may not be
I get it,
the same one. So
I get what you're trying to
all of their, of course, yeah. all of the triangulation nets are diagrammed in that book. Again, this is the triangulation of the American arc of the parallel. And then these are the measurements of the triangles. These are the angles of the triangles that they measured using theodolites. He is 53 degrees, 38 arc minutes, 37.117 arc seconds. Pilot peak is 91, right?
59.
They sum.
I'm adding up right now, yeah.
Yep. They sum to 62 arc seconds more than 180 degrees. That's what that 62.160 is at the bottom. You see that?
Oh, okay. Then I don't even need to. Okay.
Yeah. So that particular triangle sums to more than 180 degrees.
How much is that in degrees?
Well,
from the top of my head.
An arc second is 1/3600th. An arc minute is 1/60th. So that's 62 arc seconds, which is just a tiny bit more than 1 arc minute. So let's just call it 1 arc minute. So that's 1/60th of a degree more than 180 degrees. But you can see they carried 3 digits of precision.
0.17.
Yeah, but you can see they carried 3 digits of precision in after their arc second measurement. So this particular margin of error is extremely small. It's much, much less than 1 arc second. So this particular measurement is almost 2 orders of magnitude larger than the margin of error. So it's a significant
where is the margin of error in this image?
Yeah, you can see that they have 3 digits of precision after the decimal point for arc seconds. Do you see that? So that 37.117, that is arc seconds. Right? So their margin of error is going to be somewhere within that final digit.
That's supposedly, yeah.
Yeah.
They didn't calculate something over and then just, claim that it must be there. It must be there. But again, that arc second is converting to 0.01 degrees. Now, will you imagine in real life that you could be off by that much when you are measuring 3 angles, one after another?
Well, like I said,
anytime I can. Yeah.
Yeah, like I said, they actually carry 3 digits of precision after the decimal point for arc seconds. So their measurement error doesn't care.
87. I just see that. 87, they had a precision of that small accuracy. Wow.
Yes.
Okay.
They were using 20-inch long telescopes. Right? Extremely precise measurements here. So the point is, I mean, if you want to just declare, hand wave that they couldn't possibly do it, then you go right ahead. But denialism isn't evidence; it's just denialism. So you feel free to look through this particular documentation. It's quite thorough. It's 900 pages. The thing is, every one of these. Right. So if they're off on one, well, then the next one and the next one and the next one and the next, they're over 180 degrees on every one of these triangles. You see that?
By 0.012 degrees.
Yeah. And
I do see that.
And their instruments are able to measure significantly more precise than that. So all of these are more than 180 degrees, showing that these are not planar triangles. It is not possible on a plane for a triangle to have more than 180 degrees. These do have more than 180 degrees. Therefore, they are not planar triangles.
Again, I still have a contention to that because it's 1887 and we are talking about a very small amount of margin of error.
Do you have any evidence?
Way within the human error.
Do you have any evidence that their margin of error is
even
wrong?
The human error?
Do you have any evidence that other than
within the human error?
It sounds like all you have is denialism. You don't have any evidence for this.
I might have for next time if we would ever have, but from the top of my head, I cannot show it to you right now.
I have sent this particular document to many, many flat earthers. They always say they're going to have a look, and they come back. Well, they never come back. So
that's a good story.
Hey, maybe you'll be the first. Again, that's on my website. You can download it from there, or there's a link to the original source. My website, mc2.net/r. It's the 5th measurement of the radius of the Earth listed on that page. All right. But I do appreciate that Chadwick one that you sent. I will have a look at that and see if I can get the source data, because it looks like the same types of triangulation net maps.
Okay. I think it's been 2 hours, and I really do think, by the way, that the audience is getting more and more bored.
Yeah, I understand. I think it's a good time. I'll even unmute Crux so he can so I can hear him next time.
Okay.
So I just wanted to say, sorry, before Amy jumps in, I just wanted to say that thank you, McToon, for being civil about all of this.
Yeah, thank you. And we get hot, and I think if we can come out of it smiling, I think it's a good idea.
Absolutely. And I do want to thank you both for coming and doing such a great job and staying so calm for the whole 2 hours. That's amazing. So thank you both for that. I also want to thank everybody in the chat for commenting and having good pictures coming up and links and everything. And I want to thank everyone's patience in the stream itself in the VC. And I want to thank our gracious hosts too for having us on and being so wonderful about it. This is a great platform, so thank you for that too. Thank you.
And I would like to thank you, Amy, also for moderating the debate, which didn't take much today, at least.
No, it didn't. And thank you very much. I appreciate it. You both did a great job. Both of you did. So thank you for that. And I've learned something from both of you. So that's awesome. Thank you.
Thanks a lot. Thanks, Whatsup, and Amy and Bev. If you're still here, thank you for facilitating this.
Yes, absolutely. Thank you. Thank you for hosting us.
No, I don't hear him talking.
Everybody have a good night.
He's still there. Yeah, all right. We'll see you later. There you have it, the debate. I hope you enjoyed it. I will be back next week. I already have something in the works. And thank you to members and patrons. And it just wouldn't be a Tuesday night without the outro roll.